Hey there, Python programmers. Today we have a really interesting video in our tic-tac-toe series for a couple reasons. One reason is I'm not going to write any code in this one. We really need to talk about like the idea behind how we are going to get a computer to play us in tic-tac-toe. The other interesting thing is I'm going to draw, and that can always be entertaining. So let's jump into talking about, again, how we are going to make our computer player work. Now here we have a game scenario. We're going to say, hey, the first player is already moved, and let's again just pretend they are human. They have made a decision and put an X in the middle. It's honestly how I start most tic-tac-toe games, so again, I'd say pretty common. So now would be the computer's turn. So our computer needs to decide where it's going to move. And honestly, for the first move, it kind of doesn't matter too much because, again, no matter where that computer moves the first time, it can't lose. We don't have enough pieces played. So, honestly, the first time doesn't matter. But the second time, once our player's gotten to go again, there could be a possibility that if the computer does not make the right move, it's going to lose. So, how is this all going to happen? So we need to talk about something called a decision tree, because that is also going to hopefully help us explain a little bit how this works. So a decision tree is a way of mapping out how certain, scenarios can happen. It works really good for tic-tac-toe. You can do it for chess too, but it becomes pretty complicated. So let's start. In this decision tree, one decision has already been made because our players already played X. So now it's O's turn. Technically, O has 8 different possibilities of how it could play. It can pick the top corner, can pick the top middle, it can pick the other top corner, or we could entirely go down to the second row. And this would continue on. So again, for every possible move, and at this point, we should actually have 8, right? Because there are only 8 places to move. So this is the start, 1, 2, 3, of our decision tree. 8 different decisions. Now, let's say we advance. Let's say O decides to play, just for drawing's sake, O plays here. Cool. So we have selected this one. From here now, there are 7 decisions for where X is going to play next. Boom, boom, boom. Again, we have X. At this point, O has played here. Maybe X is going to play here. Boom, boom, boom. And again, I'll draw just a few of the scenarios where X could have gone. We won't do every single one, but ultimately, there are going to be, so we did 3. At this point, there will be 7 choices for where we come here. See, it's already getting messy. Okay, so let's now decide that, hey, this move was picked. We put an X here. This is our game board. Guess what? Now we have 6 new options coming out from here. And again, this will be our final level of example because it looks like I'm going to run out of room. And at this point, again, every one of these scenarios has to be what we picked from above, but where O plays its next move. And this is actually going to be enough for us to start to see our scenario. So we actually now have a couple scenarios, or multiple scenarios, where if O does not pick the right place, it could lose on the next move, right? Right now, X could potentially win. So if we do not pick here, again, we might check out the different possibilities. Like there's no reason to say we couldn't play here or we couldn't play here, but those are going to have some interesting consequences. So kind of each time we go down the level of this tree, there are going to be less possibilities, but actually overall more possibilities because we are only drawing out the ones that we actually kind of chose to prove go forward. But every single one of these first eight is going to have a tree coming off of it, like what we did for the one right here. So, a couple things this tells us. First of all, because this information is in a tree, if we want to traverse this tree, going down the different nodes to find values, or anytime we want to traverse a tree, that's going to be a recursive type problem. Again, how we're going to solve this problem is something called a minimax. That is a recursive function we will be writing. So again, that's where we are headed. Now, if we have a couple things, if we have the ability to kind of provide the game board or the state of the game, which we do because we want to remember that we are keeping track of our game board in a variable in our class called self.board. And if we have a function that checks like the status of the board and can tell us what is the win, and we also have that in our check for win function method, those things combined are things we can provide our computer to actually start playing and become actually quite unbeatable. So we've seen there are scenarios where, like right here, this is critical. If O does not play here on the next move, it's very likely that X will take that, and that would result in a win. And at that point, O loses. That's not good. So, what we'll have our computer do, and again, we have two methods we're going to use. One will be starting a computer play. And pretty much when the computer takes over, it's given the board, it is going to go through the board piece by piece. If that's empty, the computer can do a decision tree based on if I move here, how can the game play out? It can then do that for any other open space. Now, if we have already a move there, we won't tell the computer to do it because, again, that would be wasteful. There's already a move there. But we can feed the computer the board so it knows how it's. Basically, we're feeding the computer the state of the game and we're giving it a method it can use to tell if it's won or not. And we can use those to make this computer unbeatable. And again, because our computers are super fast, it's going to go through and play out every scenario of the game it can possibly do. And all we kind of have to do is provide some sort of metric or score. So again, like if it goes through and gets to this is a losing scenario right here. This would be bad, so maybe we'll assign this -10 points. And somewhere down the tree over here, there's going to be a scenario where we win, and we can assign that to be +10 points. And now what'll happen is each potential move the computer can do, it can kind of follow this decision tree and have a result. So again, it will know if I move here, and again, a lot of these are ties. So if I move here, I won't lose. Okay, that's a good one. But again, this scenario here, we had to have the fact that if O didn't come here, I would lose. So there's basically a end scenario for the computer of moving here would cause me to have -10 points, and I don't want that. I want to go in places that either kind of end in a zero, and that would be a tie, right? Because a lot of these scenarios will result in ties. Ties are better than losing, but not as good as winning. So equipped with all these tools and pieces, we'll be able to go ahead and make a really smart computer that again is going to be able to, each time a player moves, or even another computer, it's going to play out every remaining scenario and find the one that gives it the best score, and it's going to use that. And so we're going to see this implemented in our next couple of videos when we tackle those last two methods. Hope you enjoy the video, like and subscribe, and I will see you in the next one.